Imagine you're watching this hyper-realistic AI-generated video of a bustling city street, right? And a sleek red sports car speeds past the camera, drifts around a corner, and just disappears behind a skyscraper.
Right, goes out of frame.
Exactly. And you, as a viewer, you expect it to emerge on the other side, but when it finally does, it's inexplicably morphed into a blue minivan. Or, sometimes it just never reappears at all.
Yeah, it is the ultimate illusion breaker. I mean, you are literally witnessing a multi-billion parameter foundation model completely fail at the basic concept of object permanence, which is a cognitive milestone that human toddlers master by their first birthday.
It's wild. So, fellow tech enthusiasts, welcome to AI Paper Slop. We are doing a highly technical deep dive today into a paper that attempts to solve this exact bottleneck. It's called WorldDirector, Building Controllable World Simulators with Persistent Dynamic Memory by Hanlin Wang, and a research team from HKU's EST, Ant Group, ZJU, and CUHK.
And just to give you all the immediate core takeaway right up front, current foundational video models, whether you're looking at Sora or Genie or whatever, they fundamentally fail because they incorrectly entangle physical dynamics with pixel rendering.
Right. They try to guess what physics should look like based purely on visual patterns.
Exactly. And WorldDirector solves this by explicitly decoupling the semantic motion orchestration from the visual rendering process.
And the architecture they propose is just fascinating. I mean, they actually utilize a large language model, specifically Gemini in this case, as a sort of makeshift game engine.
Yeah, to orchestrate continuous 3D bounding boxes and camera paths completely behind the scenes.
Right. And then those 3D paths are projected down into 2D location conditions, basically color-coded masks, which are then fed into a diffusion model alongside this really highly engineered appearance binding mechanism.
The end result being this auto-regressive, chunk-based video generator that can synthesize infinite sequences. And dynamic objects actually maintain strict physical logic and exact visual identities, even after being hidden from the camera for a long time.
Which is huge. So let's unpack why this has been such an insurmountable roadblock for the whole video generation field up until now. Because, the entire industry is trying to navigate this paradigm shift from passive pixel synthesis to, interactive world simulators.
And if you want a simulator, you need the world to actually continue existing when you look away.
Right.
When current models attempt to simulate out-of-sight dynamics, they're forced to rely entirely on internal generative priors. They're essentially flying blind.
It's like asking a traditional artist to paint a bustling city while only looking through a keyhole. If a car drives past the keyhole, the artist just assumes it literally ceased to exist.
That is a perfect analogy. That implicit estimation might hold up for a second or two, but it mathematically collapses over prolonged occlusions. You see trajectory collapse, objects just freezing in a latent state, or severe identity distortion upon re-entry.
And I know previous architectures tried to fix this by, implementing explicit monitors for off-screen objects.
Yeah, they would run separate parallel tracking algorithms for every single entity not currently in the frame.
Which just sounds like a complete computational nightmare. I mean, if you have a busy highway scene with 50 dynamic entities, scaling a dedicated tracking monitor for every single occluded vehicle would just melt your VRAM.
Oh, absolutely.
But let me push back a bit here. If the diffusion model's entire purpose is just denoising the next set of pixels in the frame, how is it even possible to force it to calculate off-screen 3D physics without bolting a heavy, traditional video game physics engine directly onto it?
Well, you avoid bolting anything onto the diffusion model by taking the physics calculation away from the pixel generator entirely. That is the critical architectural insight of WorldDirector.
Okay, so you just don't ask the diffusion model to understand physics at all.
Right, you hand it a deterministic map of the physics.
Let's trace how that data actually flows. The pipeline starts with this first major stage, what the authors call world planning via LLM.
Yeah, so given an initial starting frame of the video, the framework utilizes vision tools. They use SAM3 and Depth Anything V2 to extract rough 3D bounding boxes of all the relevant objects in the scene.
Got it. Which grounds the system in the actual visual geometry of the frame rather than asking a language model to just hallucinate a starting state from scratch.
Exactly. So you have these initial 3D anchor points.
Yeah.
Then the LLM is prompted with exact OpenGL coordinate systems, camera intrinsics, and axis ground heights.
And then you provide a text prompt detailing what should happen. You say, the car drives behind the building and the camera pans left.
The language model then scripts out the continuous 3D trajectories and camera poses for the entire duration of the generation.
Now wait, I find it highly counterintuitive to use a language model as a rudimentary physics engine. LLMs are notoriously bad at spatial geometry and complex math. Asking an LLM to calculate continuous, intersecting 3D bounding box trajectories over hundreds of frames, that feels like asking a calculator to write poetry.
It definitely feels like a category error at first glance. However, LLMs handle this spatial logic surprisingly well when you structure the prompt with strict deterministic constraints.
Really? Just by structuring the prompt?
Yeah. By forcing the LLM to operate within defined OpenGL coordinates, specific ground planes, and precise camera parameters, it doesn't have to visually render anything. It's merely outputting the raw algebraic transformations of where a coordinate box should exist at, say, frame 120, based on a defined velocity vector.
Ah, I see. So it's just predicting the next mathematical token in a sequence of geometric transformations.
Precisely.
But once the LLM generates those 3D paths, there has to be some sort of translation layer, right? Diffusion models natively operate in 2D pixel space, so 3D coordinates mean literally or nothing to the UNet.
That's right. So those 3D paths are mathematically projected down into a sequence of 2D bounding boxes based on the generated camera perspective. The paper refers to this as location condition B.
Location condition B.
For the diffusion model, this translates into a series of color-coded masks on a black background. And that dictates exactly where an object's pixels should be constrained within any given frame.
Okay, so the model now has this flawless spatial layout. It knows exactly where the objects are when they re-enter the camera's view. But the next hurdle has to be memory.
Memory is the big one, yes.
Right, because if the LLM simply outputs a mask saying, the red car goes here, how does the video model remember that that specific car had mud on the tires and a dent in the fender?
That is handled by the appearance condition, which they designate as condition A. The model actively retrieves RGB features of the objects from the contextual history of the generated video.
Oh, so it looks back at what it already made.
Exactly. When an object is scheduled by the LLM to re-enter the frame, the system pulls a high-fidelity reference crop of that exact object from a previous frame where it was clearly visible. And it maps that reference crop to the coordinates of the newly projected 2D bounding box.
But wait, if you constantly feed a latent diffusion model the exact visual features of an object for every single frame, it's just going to get lazy, right? It's going to stop generating new motion.
Yes, 100%.
You'd end up with a very stiff robotic video where just a static JPEG of a car is being dragged across the screen.
Yeah, that phenomenon is known in the field as sliding artifacts. The model gets incredibly lazy. If you provide dense visual conditioning in every frame, the network relies entirely on that RGB feature map rather than actively generating articulated motion.
So a character will just glide across the screen without moving their legs.
Right, because the model doesn't need to hallucinate the leg movement. It already had the pixels it needs to satisfy the loss function.
So how do they force the model to actually animate the object then?
They introduce something called the temporal drop mechanism.
Temporal drop mechanism. Sounds intense.
It's super clever. When a newly entering object appears, the system provides dense reference frames for the first 16 frames to establish the visual identity.
Okay, anchoring it.
Right. But after that initial anchor, it drops the frequency down dramatically, providing just one reference frame every 6 frames. For the gaps in between, the appearance condition is replaced entirely with null embeddings.
Ah, so it operates very much like keyframe animation in traditional graphics. You hand the model the character reference sheet every few seconds to anchor the identity, but you starve it of visual data in between.
Exactly. And by starving the network of visual data for those in-between frames, you literally force the diffusion model to do the heavy lifting of animating the articulated motion.
Like spinning the wheels, moving the legs, shifting the lighting reflections.
Yes, guided by the spatial trajectories and the semantic text prompt. Architecturally, both the location masks and these sparse appearance features are encoded by a 3D variational autoencoder and concatenated directly with the noisy latents.
Wow. Which neatly solves the generation problem for a short sequence. We have the LLM mapping the location and the temporal drop mechanism anchoring the appearance.
Yep.
But this paper claims to achieve long horizon, potentially infinite generation. How on earth does a diffusion architecture scale to a 15-second simulation, let alone infinite, without blowing out the GPU memory or just decaying into a blurry hallucinatory mess?
Well, they implement a causal, autoregressive, chunk-based generation strategy. They don't even attempt to generate 15 or 30 seconds of video simultaneously.
That would just fry the hardware.
Oh, absolutely. The video is generated in manageable 5-second chunks. To maintain perfect continuity from chunk 1 to chunk 2, the system retrieves 10 context frames from the previously generated history.
Okay, so that serves as a memory buffer.
Right, which they call context M.
But selecting those 10 frames seems critical. I mean, if the camera has been panning rapidly around a complex street scene for a full minute, 10 frames of memory is an incredibly narrow bottleneck.
It is, which is why it requires a highly deliberate, dual-perspective context retrieval system. They don't just grab the last 10 sequential frames. First, they gather static context.
How does that work?
The system scans the historical frames and selects those that have the maximum field of view overlap with the current camera position being generated.
Oh, okay. So this guarantees that background elements like buildings or mountains remain perfectly stable even if you look away and look back.
Precisely. And then, for the moving objects, they use dynamic context retrieval. It utilizes a greedy algorithm that scans the history to ensure every single dynamic entity's bounding box has maximum coverage in the memory buffer.
So they interleave these static and dynamic frames.
Exactly. They interleave them, enforce a minimum temporal stride so you aren't just getting 10 frames from the exact same second of video, and that synthesized batch becomes the context buffer.
That's super elegant.
But the real engineering magic happens when they inject that clean memory into the diffusion process. The 10 context frames are concatenated along the temporal axis with the noisy latence of the current chunk being generated.
Right. But in a standard attention mechanism, the model looks at everything simultaneously, doesn't it? If you mix clean, high-fidelity historical frames with the noisy, chaotic frames the model is actively trying to denoise, the model's going to get mathematically confused.
Yes, the training noise will bleed over and completely pollute the context.
So how do they stop that pollution?
They use an asymmetric attention mask. It essentially creates a one-way mirror in the latent space. The context tokens only self-attend.
Okay, so the current noisy tokens are allowed to look back at the context frames for reference, but the context frames cannot mathematically see the noise of the present.
Exactly. And they take it a step further at the positional embedding level. You're likely familiar with ROPE, or rotary position embedding, which injects relative sequence information into the attention mechanism.
Right, it acts as the mathematical clock so the model understands the order of events.
Well, in WorldDirector, they apply a massive artificial offset to the ROPE time steps for the context frames.
Wait, a massive offset. So by applying that offset, you are effectively putting the historical memory in a completely different time zone than the current video being generated.
Yes. It creates a strict frequency boundary in the latent space, explicitly disentangling the historical anchors from the generative chunk.
Wow. So the model fundamentally understands at an architectural level, like, this data is untouchable memory, use it as a reference anchor, but do not attempt to alter or denoise it.
Exactly.
That structural separation of past and present is just brilliant. So the memory keeps the established world stable. But what about actually directing the action? Because the fusion models are notoriously prone to attribute leakage.
Oh yeah, the classic prompt bleeding problem.
Right. If you have a complex prompt describing a sleek sports car driving past a fluffy dog running on the sidewalk, the model will so often accidentally apply the furry texture to the car. How do you ensure semantic control over multiple distinct entities?
They mitigate attribute leakage by implementing a spatial-aware weighted cross-attention mechanism.
Spatial-aware weighted cross-attention.
Yes. Normally, cross-attention between the text prompt and the visual latents is computed globally across the entire frame. The model searches everywhere for the dog or the car. But in WorldDirector, they intercept and bias the pre-softmax attention logits.
So they use the 2D bounding box trajectories projected from the LLM and mathematically route the specific text tokens describing an entity exclusively to the visual tokens inside that entity's bounding box.
Yes. The word dog is mathematically constrained.
Right.
It is only permitted to influence the pixels inside the dog's localized trajectory.
That completely isolates the semantic control.
And this spatial awareness unlocks what is arguably the most powerful capability of the entire framework. promptable world events.
Promptable world events.
Because the LLM acts as an omniscient world planner, the system is no longer constrained by the assets that were visible in the very first frame of the video.
Oh, wait, really? So you can dynamically introduce entirely new elements mid-generation?
Yes. If you are simulating a street scene for 10 seconds, at second 11, you can simply prompt the LLM to spawn a helicopter flying overhead.
That is so cool. So the LLM instantly synthesizes a new 3D entrance trajectory for the helicopter. And then when that trajectory intersects with the camera's view, its initial appearance is generated directly from the text prompt via the diffusion model.
Exactly. And from that moment forward, its visual features are recursively tracked and fed into the appearance condition pool, just like the original objects in the scene.
So it transitions from simple video extrapolation into true event orchestration. I mean, you can script an evolving narrative. You could even execute seamless transitions from a third-person to a first-person viewpoint simply by prompting the LLM to detach the camera path from the main subject and push it into a first-person perspective.
Right, because the rendering engine simply follows the math. You're getting the precise directorial control of a traditional 3D rendering engine like Unreal, but combined with the photorealism and infinite asset generation capabilities of a foundational diffusion model.
That is insane. But okay, to train a model to execute this level of complex object permanence, standard datasets have to be useless. Scraping random YouTube videos won't work because real-world video is messy, unstructured, and it entirely lacks the explicit ground truth data of what is happening to objects when they are occluded by, say, a wall or a passing bus.
That was a huge bottleneck for them. The researchers had to build a highly specialized synthetic data pipeline, completely from scratch.
How do they do it?
They utilized a game-based platform to procedurally generate 15-second videos that were deliberately scripted to induce complex disappearances and reappearances of target objects.
Oh, so they forced the model to learn object permanence by feeding it thousands of controlled examples of entities hiding behind obstacles and emerging later.
Exactly. And they used SAM-3 to track the precise 2D bounding boxes across these temporary exits, ensuring the identities were flawlessly annotated even during the occlusion.
Right. And then what? They superimposed these color-coded bounding boxes onto the source frames and fed the entire visual sequence into Qwen 2.5 VL72B?
You got it. Which is a massive state-of-the-art vision language model. Qwen 2.5 generated highly fine-grained textual captions detailing every single entity's action dynamics, spatial relationships, and temporal changes across those 15-second clips.
So this gave the diffusion model an impeccably clean, dense dataset correlating text, spatial masks, and temporal permanence.
Yep. And the benchmarks really reflect the quality of that pipeline. When tested against current state-of-the-art baselines, models like Hume, HY World, Infinite World, High DRA, and Lingbot WorldDirector, outperforms them significantly on standard metrics like PSNR and SM.
But where it truly dominates is the dynamic subject consistency metric, or DSC.
Right. DSC uses DINO and CLIP embeddings to measure if a dynamic object retains its exact visual identity after it reappears from an occlusion.
So if you test a purely generative baseline like High DRA, and you have a character walk off screen, wait 5 seconds, and pan the camera back, High DRA will almost certainly generate a completely different person wearing different clothes.
Almost every time. But WorldDirector preserves the exact identity embeddings across the occlusion gap.
When you dig into the evaluation tables in the paper, there is actually a hilarious anomaly I noticed.
Oh, the background consistency one.
Yes. Baselines like Hume or Infinite World scored surprisingly well on the background consistency metric. But the researchers point out that this high score is purely a mirage.
Yeah, it's so funny.
Those models fail to generate any meaningful subject movement or camera motion. They basically just output a static image for 15 seconds. It is incredibly easy to keep the background mathematically consistent when your model accidentally freezes the entire video into a JPEG.
It is a textbook example of an AI model gaming a metric by doing absolutely nothing.
Exactly. WorldDirector, by contrast, achieves superior consistency while simultaneously executing highly dynamic, complex, user-prompted camera sweeps and subject movements.
Which really brings us full circle. The industry is rapidly migrating from hallucinating pixel generators to true physics-aware interactive simulators. Decoupling the semantic intent from the pixel rendering is undeniably the blueprint for the next generation of video models.
Right, because by forcing the diffusion network to adhere to an external, logically consistent 3D plan, you eliminate the compounding errors that inevitably destroy purely generative approaches.
You gain temporal stability, you solve object permanence, and you hand unprecedented directorial control to the user. It really is a fundamental architectural shift.
It's massive. And if explicitly decoupling spatial planning from rendering solves the permanence problem, the logical next step is exploring alternative spatial planners. Right now, this paper uses an LLM to orchestrate the bounding boxes. But what happens when you replace the LLM with real-time data feeds?
Oh, that's an interesting thought.
Right. Consider the implications for live sports. Could you soon have a video world model dynamically generating a photorealistic multi-camera live broadcast of a Formula One race or an NFL game, driven entirely by the live 3D telemetry data streaming directly from the cars or the player's shoulder pads?
Wow. Yeah, once the rendering engine is decouples from the physics engine, the source of that physics data can be anything, an LLM, a video game, or real-world sensors. The possibilities for live, interactive, synthetic media generation are pretty staggering.
It's going to be a wild couple of years. We will be closely monitoring how this architecture scales in the coming months. Thank you for joining us on this deep dive into the underlying mechanics of AI paper slop. Keep dissecting the research and stay technical.